Hello and welcome to T Academy with another lecture on signals and systems. In today's lecture, we'll be talking about eigenfunctions and how we can arrive at Fourier series representation using complex exponentials and their peculiar property of being an eigenfunction of an LTI system. So we'll proceed with the well-known convolution equation in the continuous time, which says that the output y of t is integral minus infinity to infinity h of tau x of t minus tau d tau, where h of tau is the impulse response of the system and x of t is the input. Now this peculiar property of being an eigenfunction of an LTI system arises when the input x of t is chosen as a complex exponential e to the power st. Now I looked at detail in one of my previous lectures on complex exponentials and their properties, in particular the property of periodicity. So if you are interested in that lecture, you can click the link and watch it. Now if I substitute e to the power st into this equation, I will get integral minus infinity to infinity h of tau e to the power s of t minus tau d tau. Now e to the power st is independent of the integrating variable tau, so I can take it outside of the integral and write as e to the power st times the integral minus infinity to infinity h of tau e to the power minus s of tau. Now as you can see, this integral, it depends only on the complex exponential s and the integrating variable tau. Thus, as far as the independent variable t is concerned, this is a constant. Thus, I can write y of t is equal to e to the power st times h of s, which is a constant. And now we can arrive at a formal definition of eigenfunction. So eigenfunction is a signal for which the system output is a constant times the input, and this signal is known as the eigenfunction of the system, and the associated amplitude factor h of s in this case is known as the eigenvalue of the system. So let's write this equation once again to bring the point home. We have y of t is equal to e to the power st times h of s, where h of s is equal to integral minus infinity to infinity h of tau e to the power minus s of tau. So from this analysis, we find out that the complex exponential e to the power st is an eigenfunction for LTI systems. Remember that the convolution theorem is valid only for linear time invariant systems, and it has a corresponding eigenvalue h of s, which is the integral of the impulse response times e to the power minus s of tau. Now how does this allow us to arrive at the Fourier series representation? So for Fourier series representation, we can write our input as a sum of complex exponentials. So for instance, if the input is given as a1 e to the power s1 of t plus a2 times e to the power s2 times t plus a3 times e to the power s3 times t, then I can write the output y of t as a1 times e to the power s1t. So this is the eigenfunction, since we know that a complex exponential is an eigenfunction, times its corresponding eigenvalue, which would be h of s1. And using the principle of superposition, which is valid for linear systems, I can do it for all the three components of the input. So a2 times e to the power s2 times t times h of s2 plus a3 times e to the power s3 t times h of s3. Thus, if I can write my input x of t as a summation of complex exponentials, summation ak e to the power sk times t, then the output y of t is a summation over k of the same complex exponentials times their corresponding eigenvalues. And this here is the basis of Fourier series representation, where the input is written as a summation of complex exponentials, and corresponding to each complex exponential there is an eigenvalue, and once we find out that eigenvalue, we can find out the response of the total system. Now let's see this with an example. Suppose we have this relation that the output y of t is equal to the input delayed by 3. So I have covered delay operation, time shifting and time reversal in one of my previous videos. You can click the link and watch that lecture if you are interested. The input to this system is a complex exponential e to the power j2 t, and here we have used s is equal to j2, where 2 is the angular frequency. Now if I substitute this into this equation, I will get e to the power j2 times t minus 3, which can be written as e to the power j2 times t times e to the power minus 6j. And it is quite straightforward to see from here that the eigenvalue of the system h of j2 is equal to e minus j6 for the eigenfunction e to the power j2t. But we can also find this using the expression that we derived, that h of s is equal to integral minus infinity to infinity h of tau e to the power minus s tau d tau. Now since we know that the impulse response of the system for an input x of t is found out by replacing x of t with delta of t, so I will write here delta of t minus 3 times e to the power minus s of tau d tau integral minus infinity to infinity And here, using the shifting property, we can find this out as e to the power minus 3s, since this integral is only valid for t equals to 3. So this is h of s, and if I were to find out h of j2, I would simply get e to the power minus j6, which is the eigenvalue which we found out from inspection. So that's it for today's lecture. We saw how we can arrive at Fourier series representation using the property of eigenfunctions and eigenvalues. And we will continue further with our lecture series on signals and systems. If you have any questions or suggestions for future videos, please do write in the comment section, and I hope to see you in another lecture. Bye.